There is a number that keeps astronomers awake at night, not because it is difficult to calculate, not because the instruments are broken or the data is corrupted, but because the number is correct and it shouldn't be. The number is a redshift, a measure of how far light has been stretched on its journey across the universe. And when astronomers pointed the James Webb Space Telescope toward a faint smudge of light in the sky, a smudge so dim it had never been resolved before, never been examined in any meaningful detail, and when they ran the spectroscopy and watched the data come back, what they found was a galaxy sitting at a distance so extreme, so incomprehensibly remote, that it forces us to confront something deeply uncomfortable about what we thought we understood, not just about that galaxy, about all of them. Because the problem isn't simply that the galaxy is far away. The universe is vast, and distance alone is no longer surprising. The problem is what the galaxy looks like at that distance. The problem is what it implies about when stars first began to burn, when matter first gathered itself into coherent structure, when the universe, raw, young, and supposedly chaotic, decided to organize itself in ways that our best models say it simply could not have done so quickly. What the Webb telescope has been doing since it opened its golden mirror to the infrared sky is systematically dismantling a comfortable picture. One observation at a time, one redshift measurement at a time, it has been sending back data that challenges the foundational assumptions of modern cosmology. And the galaxy we're going to talk about today, this one faint signal from the edge of observable time, is among the most confrontational pieces of evidence yet. If you enjoy deep space explorations like this, consider subscribing. To understand what makes this discovery so unsettling, we first have to understand what the universe is supposed to have looked like at that age. And to understand that, we need to go back to the very beginning, not metaphorically, but literally, to the first moments after the Big Bang, when everything that would ever exist was compressed into a space smaller than anything our intuitions are capable of grasping. Approximately 13.8 billion years ago, the universe was not a place, it was a state of almost incomprehensible density and temperature, where the laws of physics as we know them barely apply, where space and time themselves were tangled in a configuration we cannot fully model, and then, in whatever sense the word applies to something that has no before, it expanded, not into existing space. There was no existing space. Space itself expanded, carrying matter and energy with it, and as it did, it cooled. For the first few 100,000 years, the universe was so hot that atoms could not hold themselves together. Electrons were constantly being knocked free of protons by the ambient energy of the environment. The universe was a plasma, an opaque, glowing fog of charged particles that light could not pass through. This is why we can't see further back in time than a certain point. The earliest light we can detect is the cosmic microwave background radiation, a faint glow of microwaves that permeates the entire sky, the afterglow of the moment when the universe finally cooled enough for atoms to form, for electrons to bind to protons, for matter to become transparent to light. This moment is called recombination, and it happened roughly 380,000 years after the Big Bang. After recombination, the universe went dark. Literally, there were no stars yet. There were no galaxies. There was only hydrogen and helium, slowly being pulled together by gravity, forming clumps and filaments in the cosmic web that gravity was quietly, patiently assembling. This period is called the Cosmic Dark Ages, and by every model we have constructed based on the physics of structure formation, it should have lasted a while, not forever, but long enough. The first stars, population 3 stars, astronomers call them, were not like the stars we see today. They were formed from pure primordial hydrogen and helium, with no heavier elements at all, because heavier elements had not yet been forged in any stellar furnace and dispersed by any supernova. These first stars were likely massive, extraordinarily luminous, and short-lived. They burned hot and fast and violent, and when they died, they seeded the universe with the first carbon, the first oxygen, the first iron, the raw material for the next generation of stars, and eventually for planets and life. The process of galaxy formation, as we've understood it, is hierarchical. Small things come first. Dark matter halos condense out of the primordial fluctuations in density, and ordinary matter, baryonic matter, The stuff we can see falls into these halos and begins to form stars. Small proto-galaxies assemble. They merge with each other. They accrete more gas. Over hundreds of millions and then billions of years, the large, complex structured galaxies we see in the local universe take shape. This picture, hierarchical structure formation within a universe dominated by cold, dark matter and dark energy, what cosmologists call lambda CDM, has been extraordinarily successful. It has made predictions that matched observations for decades. It explains the large-scale structure of the universe, the distribution of galaxies in filaments and sheets and voids, the statistics of galaxy sizes and types. It is the standard model of cosmology, and it was built not casually but rigorously over generations of theoretical work and observation. And then Webb looked at the early universe and started finding things that, according to lambda CDM, should not have been there. The galaxy that prompted some of the most intense discussion was first identified through a combination of deep field imaging and spectroscopic follow-up. Spectroscopy is how astronomers confirm distances in deep space. When you look at a distant galaxy, the light you receive has been stretched by the expansion of the universe. The longer it has been traveling, the more it has been stretched. This stretching shifts the spectral lines, the characteristic absorption and emission features that different elements produce, toward the red end of the spectrum. The redshift is a direct measure of how much the universe has expanded since that light was emitted, and from that, astronomers can calculate the distance and the age of the universe at the time the light left its source. When Webb's near-infrared spectrograph locked onto this galaxy and began pulling apart its light, the redshift that came back was staggering. We're talking about a galaxy whose light was emitted when the universe was only a few 100 million years old, in the range of 300 to 500 million years after the Big Bang, depending on the specific target. Some of the candidates Webb has identified push even closer to that edge. Some have claimed tentative detections that, if confirmed, would put us at a mere 200 to 300 million years post-Big Bang. But age alone isn't the scandal. The scandal is the mass. The scandal is the size. The scandal is how thoroughly, completely, maturely formed these galaxies appear to be. When astronomers look at a galaxy, they can estimate certain properties from the light it emits. The total luminosity tells you something about how many stars are present. The color of the light tells you about the ages and types of those stars. The presence or absence of certain spectral features tells you about the galaxy's star formation history, whether it is actively making new stars or whether it has, as astronomers put it, quenched, meaning star formation has largely stopped. And the morphology, the shape visible even in the blurred images from enormous distances, tells you something about the galaxy's dynamical state, whether it is a violent, irregular mess of merging material or a settled, organized structure. What Webb has found in object after object in the early universe are galaxies that look too settled, too massive, too bright, too organized, galaxies with stellar masses that, by the accounting of lambda CDM, should not have been able to accumulate that many stars in that short a time. Galaxies that in some cases appear to have already undergone substantial evolution, not just beginning to form, but having formed, processed, a generation of stars, enriched their interstellar medium with metals, and in some cases already begun to suppress their own star formation. One paper that caused a particularly sharp intake of breath across the cosmological community described a collection of galaxy candidates at very high redshift, whose combined stellar mass, the mass locked up in stars that had already formed, was difficult to reconcile with standard models. The problem was not just the individual masses, but the number density. How many of these massive and early galaxies exist per unit volume of the universe? Because even if you could argue that one enormous early galaxy was a statistical fluke, a rare, overdense region that happened to form stars with unusual efficiency, you cannot make that argument when you start finding them everywhere you look. The Webb deep fields have shown that the early universe was more densely populated with massive galaxies than any of our simulations predicted, not by a small margin, by factors that make theorists uncomfortable. Now, It is important to be precise about what this does and does not mean. Science is not done by press release. The history of astronomy is full of impossible detections that turned out, on closer inspection, to be artifacts, calibration errors, contamination from foreground sources, and misidentified spectral features that gave inflated redshifts. Some of the most extreme early Webb detections have been walked back after more careful analysis. Photometric redshifts, estimates of distance based on the overall shape of the light curve without full spectroscopic confirmation, are less reliable than spectroscopic measurements, and some of the most alarming candidates have only photometric redshifts so far. But the ones that have been spectroscopically confirmed are real. The redshifts are not mistakes. The galaxies are there. And even setting aside the most extreme outliers and focusing only on the well-confirmed observations, there is a genuine tension between what Webb is finding and what lambda CDM predicts. The question is what kind of tension it is. There are several possible responses, and they sit along a spectrum from conservative to radical. On the conservative end, you have the argument that the models are not wrong, but that our parameters are off. Perhaps we have underestimated the efficiency with which gas can be converted into stars in the early universe. Perhaps early star formation was simply more efficient than we assumed, not implausibly so, just more so than the fiducial values we plugged into our simulations. Perhaps the initial mass function of stars in the early universe, the statistical distribution of stellar masses, was different from what we observe locally, weighted toward more massive, luminous stars, which would make these early galaxies appear brighter and more massive than they actually are in terms of total star count. These are reasonable arguments, and they are being actively pursued. Adjusting the stellar initial mass function, for instance, could in principle reduce the apparent stellar masses of these early galaxies significantly, making them more compatible with standard cosmology. If early stars were systematically more massive, they would produce more light per unit of stellar mass, meaning a galaxy that looks very massive, based on its luminosity, might actually have considerably fewer stars than the raw numbers suggest. Similarly, there are arguments about the role of active galactic nuclei, the supermassive black holes at the centers of many galaxies, when they are actively accreting material and radiating enormously. An AGN can outshine the entire stellar population of a galaxy, and if we mistake AGN light for stellar light, we will badly overestimate the galaxy's stellar mass. Some of the most extreme early Webb galaxies may have significant AGN contributions that have not been properly accounted for. These are not desperate excuses. They are legitimate scientific considerations, and unraveling them requires the kind of detailed spectroscopic analysis that takes time. The Webb telescope has been producing data faster than the community can fully analyze it, and there is a real possibility that careful re-examination of some of the more alarming results will bring them back within the bounds of standard cosmology. Not because cosmology was right all along, but because the initial measurements were incomplete. But here is where the discomfort lies. Even the conservative explanations require us to revise our understanding of early universe physics in non-trivial ways. Even if we can explain the most extreme galaxies through parameter tweaking, the overall picture Webb is painting, a universe that was dramatically more structured, more active, more chemically enriched at early times than we expected, is pushing the standard model to its limits. And some researchers are starting to ask whether the limits are being breached. The more radical end of the spectrum involves entertaining the possibility that lambda CDM itself needs modification, not replacement. The theory has too many successes for any serious scientist to advocate throwing it out, but modification. There may be physics operating in the early universe that our models do not capture. There may be processes involving dark matter that differ from our standard assumptions about its behavior. There may be aspects of early universe physics that we simply haven't modeled correctly. One particularly intriguing line of thought concerns the nature of dark matter itself. In the standard lambda CDM model, dark matter is cold, meaning that its particles have velocities that are much smaller than the speed of light, so they can clump together on small scales and form the dense halos that seed galaxy formation. This is a critical property. Cold dark matter forms structure efficiently, which is why the model is so successful at explaining the large-scale structure of the universe. But what if dark matter has properties we haven't accounted for? What if there are interactions within the dark matter sector, dark matter particles interacting with each other in ways that have no counterpart in the standard model of particle physics, that could accelerate or modify early structure formation? There is a whole literature on self-interacting dark matter, fuzzy dark matter, warm dark matter, and various other modifications to the cold dark matter paradigm, each with different implications for how structure forms in the early universe. Most of these alternatives were designed to address problems at small scales, the so-called small-scale structure problems of lambda CDM, which include the observation that our simulations predict more small satellite galaxies around large galaxies like the Milky Way than we actually observe. But some of them also have implications for early galaxy formation, and the Webb observations are adding new constraints to this theoretical landscape. There is also the question of primordial black holes. In some scenarios, the very early universe could have produced black holes not through stellar collapse, but through direct gravitational collapse of overdense regions in the primordial plasma. These primordial black holes could, in principle, serve as seeds for early galaxy formation, providing the gravitational anchors around which matter accumulates much faster than it would in the standard picture. If primordial black holes exist in significant numbers and with appropriate mass ranges, they could go a long way toward explaining why we see such massive, structured galaxies so early. The search for primordial black holes is one of the active frontiers in cosmology and gravitational wave astronomy, and while direct evidence remains elusive, the possibility cannot be dismissed. But perhaps the most fundamental question raised by these early Webb observations is one that cosmologists prefer not to dwell on in polite company, because it touches something deeper than parameter adjustments or exotic dark matter models. The question is this: do we actually understand the initial conditions of the universe well enough to trust our predictions for early galaxy formation? The universe we observe today grew from quantum fluctuations in the early inflationary epoch, tiny variations in density that were stretched to cosmic scales by the exponential expansion of inflation, and that served as the seeds for all subsequent structure formation. The spectrum of these fluctuations, how their amplitude varies with scale, has been measured with extraordinary precision by the Planck satellite's observations of the cosmic microwave background, and those measurements underpin all of our structure formation simulations. But the connection between the CMB measurements and the actual process of galaxy formation involves a chain of physics: the growth of density perturbations under gravity, the formation of dark matter halos, the cooling and collapse of gas, the ignition of stars, the feedback from those stars and from black holes on their surrounding gas, each link of which introduces uncertainties. And when you compound uncertainties across a chain that spans from 380,000 years after the Big Bang to the present day, small errors at each step can accumulate into large discrepancies. The Webb observations are, in a very real sense, testing the entire chain. They are stress testing every assumption we have made about how structure forms, from the initial power spectrum of fluctuations to the efficiency of star formation in metal-poor environments, to the role of feedback processes in regulating galaxy growth. And they are finding that somewhere in that chain, something is not quite right. The specific galaxy that has attracted the most sustained attention in recent months, though it is far from the only one, and the field is moving so fast that any specific claim risks being superseded by the time it is read, is remarkable for several overlapping reasons. Its redshift places it at a time when the universe was not yet 500 million years old. Its inferred stellar mass is, by any reasonable analysis, extremely high for that epoch, and perhaps most surprisingly, its spectrum shows signs of enrichment with heavy elements. This last point deserves particular attention because it speaks to a fundamental constraint that no amount of initial mass function adjustment can easily circumvent. Heavy elements, carbon, oxygen, silicon, iron, all the elements heavier than helium, are made in stars. They don't exist in significant quantities in the primordial universe. They are forged in the cores of massive stars over millions of years, and then dispersed when those stars explode as supernovae. For a galaxy to show significant metal enrichment, it must have already completed at least one, and more likely several, generations of star formation. Stars had to be born, live their lives, and die, spreading their enriched material into the surrounding gas, before the next generation incorporated those metals into new stars and into the galaxy's overall chemical composition. This takes time. The minimum timescale for a massive star to live and die is a few million years, but the process of chemical enrichment, building up a galaxy's metallicity to levels detectable in its spectrum, requires many such cycles. When astronomers detect significant metallicity in a galaxy at extreme redshift, they are not just saying, there are stars there. They are saying, stars have been forming there for a substantial period of time, sufficient for multiple stellar generations to have cycled through. And that means star formation began even earlier than when we're observing this galaxy. So when Webb finds a galaxy at, say, 400 million years post-Big Bang that already shows non-trivial metal enrichment, the implication is that star formation in that system must have begun well before 400 million years, pushing back the clock for the very first stars and galaxies in ways that severely challenge what our models predict. The cosmic dark ages were supposed to last. They were supposed to provide the universe with enough time to build up structure slowly, hierarchically, patiently. Instead, Webb is showing us a universe that was in a hurry, a universe where the lights came on earlier, brighter, and in more organized configurations than anyone expected. There is a beautiful and slightly terrifying phrase that some cosmologists use when discussing this situation. They say, the early universe appears to have been over-massive, not merely more active than expected, but systematically producing galaxies with more stellar mass than the underlying dark matter halos, by the accounting of our models, should have been able to support. If you calculate, based on the abundance of dark matter halos at a given time, what the maximum total stellar mass in those halos should be, the galaxies Webb is finding appear to approach, or in some cases potentially exceed those limits. This is called the stellar-to-halo mass relation, and it is one of the bedrock predictions of galaxy formation theory. The relation encodes how efficiently dark matter halos convert available baryons into stars. It has been calibrated extensively in the local universe and at intermediate redshifts, and it has worked remarkably well. But if galaxies in the early universe are sitting above the expected relation, if they have formed more stars than their halos should permit, then either our understanding of the dark matter halo masses at those redshifts is wrong, or our understanding of star formation efficiency is wrong, or there is some source of stellar mass that we are not accounting for. None of these alternatives is comfortable. They each require revising something we thought we understood. It is worth pausing here to appreciate the instrument that is making all of this possible, because the James Webb Space Telescope is not simply a better version of what came before. It is, in several fundamental ways, a different kind of instrument, and the discoveries it is enabling could not have been made with any predecessor. Webb orbits the Sun at a special gravitational balance point known as the second Lagrange point, or L2, roughly 1.5 million kilometers from Earth in the direction away from the Sun. This location is thermally and gravitationally stable in ways that are ideal for an infrared telescope, Webb's primary mode of observation. It is shielded from the Sun, Earth, and Moon by a tennis court-sized sun shield that keeps the telescope's optics at an extraordinarily low temperature of around -233 degrees Celsius. Infrared observation requires cold instruments because any warmth in the detector or optics produces its own infrared glow that would swamp the faint signals from distant galaxies. The primary mirror, that iconic array of 18 hexagonal gold-plated beryllium segments, spans 6.5 meters, giving Webb a light-collecting area roughly 6 times larger than the Hubble Space Telescope's 2.4-meter mirror. In astronomy, collecting area is everything. More area means more photons captured in a given exposure, which means you can detect fainter objects or achieve better signal-to-noise in a given amount of time. Webb's enormous mirror, combined with its infrared sensitivity, allows it to detect galaxies that are not merely distant, but ancient galaxies whose light has been so thoroughly redshifted by the expansion of the universe that it has been pushed entirely out of the optical and into the infrared, where no previous space telescope was designed to look with comparable sensitivity. Hubble could see back to perhaps 400 to 500 million years after the Big Bang at the extreme edges of its capability. Webb routinely observes beyond that, with high-quality data at redshifts that were previously either inaccessible or achievable only with marginal detections that couldn't be verified. The frontier of observational cosmology has been pushed back by hundreds of millions of years with a single instrument, and Webb's spectrographic capability, particularly the near-infrared spectrograph NIR spec, which can simultaneously take spectra of up to 100 galaxies at once using configurable microshutters, means that the bottleneck between imaging a candidate galaxy and confirming its distance has been drastically reduced. Previous generations of telescopes required painstaking single-object spectroscopy for each galaxy. Webb can do 100 at once, and with the sensitivity to confirm redshifts for objects so faint they were previously nothing but uncertain smudges. This is why the discoveries are coming so quickly. This is why the community is sometimes struggling to keep pace with the implications. Webb is not gently probing at the edges of the observable universe. It is floodlighting a previously dark room, and what is illuminated there is not what anyone predicted. To fully appreciate the scale of the challenge Webb is posing to standard cosmology, it helps to understand what the best cosmological simulations actually predict. Over the past 2 decades, a generation of large-scale hydrodynamic simulations, projects with names like Illustris, Eagle, Simba, and most recently the TNG series, have attempted to model the formation and evolution of galaxies from just after the Big Bang to the present day. These simulations start with initial conditions derived from the cosmic microwave background measurements, include dark matter, ordinary matter, gravity, hydrodynamics, star formation, stellar feedback, black hole growth and feedback, and a host of other physical processes, and let the universe evolve forward in time within a computational box. These simulations are impressive achievements, and they reproduce many features of the observed galaxy population with striking fidelity. They get the right galaxy luminosity function at low redshift. They reproduce the bimodal distribution of galaxy colors, the correct galaxy size-mass relation, the star formation main sequence. They are validated against an enormous array of observations, and their successes are genuine. But they also make predictions for the high redshift universe, predictions for what galaxies should look like in the first billion years, and those predictions are what Webb is now testing. And the simulations, in varying degrees depending on which specific predictions you examine, are struggling. The simulations generically underpredict the number of bright, massive galaxies at very high redshift. They predict that the bright end of the galaxy luminosity function, the number of very luminous galaxies per unit volume, should be extremely low at early times, because the short available time means that only exceptionally rare regions of the universe should have been able to form such objects. But Webb is finding more bright galaxies at early times than the simulations produce, and the discrepancy appears to grow with redshift. The further back you look, the worse the mismatch becomes. This is a systematic discrepancy, not a handful of anomalies. It suggests that some physical process operating in the early universe is not correctly captured by the simulations. The question is, which one? One candidate is stellar feedback, the process by which energy from massive stars and supernovae is deposited back into the surrounding gas, heating it, potentially driving it out of the galaxy, and suppressing further star formation. In the local universe and at intermediate redshifts, stellar feedback is thought to be the primary regulator of star formation efficiency, explaining why galaxies don't convert all their available gas into stars at once. It is what prevents galaxies from being much more massive than they are. But in the early universe, the environment was different. Galaxies were smaller, denser, more gas-rich. The dynamical timescales were shorter, and there is genuine theoretical debate about whether the feedback recipes calibrated on low redshift observations correctly extrapolate to conditions in the early universe. If feedback was less effective at early times, if the high density of gas meant that stellar energy couldn't expel it as efficiently, then early galaxies could have formed stars more rapidly, building up more stellar mass in the available time. Some researchers have proposed exactly this: a feedback-free mode of star formation in the earliest, most compact, most metal-poor systems, where the conditions were so extreme that the normal regulatory mechanisms broke down and gas was converted to stars at near maximum efficiency. This would produce bursts of star formation that are qualitatively unlike anything we observe in the local universe, and they would naturally result in galaxies that appear, to Webb's instruments, strikingly overluminous and overmassive for their age. There is another piece of this puzzle that rarely gets the attention it deserves in popular discussions, and that is the relationship between these early massive galaxies and the supermassive black holes at their centers. We know from decades of observation in the local and intermediate redshift universe that essentially every large galaxy harbors a supermassive black hole at its center, and that the mass of that black hole is tightly correlated with the mass of the galaxy's stellar bulge. This relationship, the black hole galaxy coevolution, sometimes encoded in the m-sigma relation, relating black hole mass to the velocity dispersion of the surrounding stars, is one of the most striking regularities in extragalactic astronomy, and it implies that the growth of galaxies and the growth of their central black holes are intimately connected, regulated by the same feedback processes. But which comes first? Does the galaxy form and then build the black hole? Does the black hole form first and regulate the galaxy? Do they co-evolve simultaneously through some coupling we don't fully understand? In the standard picture, black holes grow through accretion, matter falling in, starting from seed black holes that are the remnants of the first massive stars, or, in some models, direct collapse black holes formed in the early universe. The problem is that the most distant quasars we know of, extraordinarily luminous, active galactic nuclei powered by supermassive black holes, exist at redshifts that place them in the first billion years, and their black holes are already billions of solar masses in size. Building a billion solar mass black hole through conventional accretion in less than a billion years, starting from a stellar remnant of a few hundred solar masses, requires either near continuous accretion at the theoretical maximum rate, what astronomers call the Eddington limit, or some way of starting with a much more massive seed. Webb is finding not just massive stellar populations at high redshift, but also evidence for massive black holes in some of these early galaxies. The combination pushes the picture harder. The accretion constraints are tighter when you have to explain both the stellar mass and the black hole mass in the available time. Some theorists have proposed a remarkable solution, that in the early universe, the first supermassive black holes formed not through stellar evolution, but through the direct collapse of massive gas clouds, bypassing the stellar phase entirely. Under the right conditions, very high ambient radiation fields that prevent the gas from cooling and fragmenting into stars, combined with the right dynamical conditions to shepherd the gas into a coherent collapse. A gas cloud of millions or even billions of solar masses could collapse directly into a black hole seed of similar mass. This direct collapse black hole scenario is speculative and theoretically demanding, but it has not been ruled out, and it would elegantly explain how the early universe built such massive black holes so quickly. The existence of direct collapse black holes would also have implications for the early galaxy population more broadly, since these massive seeds would create deep gravitational wells that attract gas and trigger star formation on accelerated timescales. A direct collapse black hole forming at, say, 200 million years post-Big Bang and then immediately driving vigorous star formation could plausibly produce the kind of massive, metal-enriched galaxy that Webb is finding at 400 to 500 million years. But even here, even in this speculative scenario, you run into timing constraints. The conditions for direct collapse require a specific and somewhat delicate set of environmental factors. the presence of intense radiation fields from nearby galaxies to suppress cooling, but not so intense as to photoionize the collapsing gas. Setting up those conditions requires some prior structure to have formed. The first galaxies are needed to irradiate the collapsing clouds that become the seeds of even larger structures. Causality constrains the chain. And this brings us to, perhaps, the deepest and most philosophically interesting aspect of what Webb is revealing. The early universe was not a simple, homogeneous place where structure grew slowly and uniformly from a nearly flat initial state. It was, from the earliest observable epoch, already heterogeneous, already differentiated, already, in some regions, intensely active in ways that we did not anticipate. The cosmic web, the large-scale filamentary structure of dark matter and gas that organizes the universe on the grandest scales, did not emerge gradually. It was already taking shape, already channeling matter into nodes and filaments, already creating the overdense regions where galaxies would form preferentially in the first few 100 million years. And those early overdensities were more extreme, apparently, than our models suggested. There is a concept in cosmology called cosmic variance, the statistical variation in the properties of the universe from one region to another, arising from the random nature of the quantum fluctuations that seeded all structure. When you observe a limited patch of sky, you are sampling one particular region of the universe, and that region may be statistically unusual, denser or less dense, more or less active in star formation than the universe average. The Webb deep fields, which look at relatively small patches of sky with extreme depth, are subject to cosmic variance. You might worry that Webb has, by chance, happened to look at an unusually overdense region of the early universe, and that this explains the apparent excess of massive early galaxies. But the fields have been designed with this concern in mind. The deep fields are spread across different parts of the sky, sampling different lines of sight, and the excess of massive early galaxies appears consistently across multiple independent fields. The statistical argument for cosmic variance as the primary explanation is becoming less and less tenable as the data accumulate. Whatever is producing the excess of massive early galaxies, it is not simply a sampling artifact. There is another dimension of the Webb discoveries that deserves its own consideration. And that is what happens after these early massive galaxies form. In the standard picture, our galaxies grow continuously throughout cosmic history, accreting gas, forming stars, occasionally merging with other galaxies. The most massive galaxies in the local universe, the giant ellipticals that sit at the centers of clusters, are the accumulated products of billions of years of mergers and accretion. They are old, but they are also the result of a long hierarchical assembly process. But some of the galaxies Webb is finding in the early universe appear to have formed the bulk of their stellar mass very quickly, and then largely stop. They are what cosmologists call massive quenched galaxies, systems that ignited early, formed stars furiously for a relatively brief period, and then had their star formation shut off, leaving a large, red, dead population of old stars that slowly fades over the subsequent billions of years. The existence of massive quenched galaxies at high redshift has been known for some time. They were detected by ground-based observatories and Hubble in earlier surveys, but Webb is finding them at higher redshifts and with higher masses than previously established, pushing the quenching problem into more extreme territory. For a galaxy to quench, to shut off star formation, something must remove or heat its gas supply so that it can no longer form new stars. The leading candidate mechanisms are AGN feedback, where energy from the central black hole drives gas out of the galaxy or prevents it from cooling, and halo heating, where the hot gas in the surrounding dark matter halo creates a thermal pressure barrier that stops cold gas from accreting. But both of these mechanisms require time to operate. AGN feedback requires a supermassive black hole to have grown to sufficient mass and luminosity. Halo heating requires the dark matter halo to be above a certain mass threshold. Both constraints are harder to satisfy in the very early universe, and yet Webb appears to be finding galaxies that have already quenched, that have already been through the entire cycle of rapid formation and shutdown, at times when our models say they should barely have begun to form. The implication if taken at face value, is that the feedback processes responsible for quenching galaxies are also accelerated in the early universe, operating on timescales that our models, calibrated on lower redshift systems, simply don't predict. Some researchers have proposed a third quenching mechanism that might be particularly relevant at high redshift: compaction-driven quenching. In this scenario, gravitational instabilities cause a galaxy to undergo a rapid, violent contraction, funneling gas toward the center and driving an intense but brief burst of star formation. The resulting compact gas-poor galaxy is then susceptible to quenching because its gas reservoir has been consumed and its high-density core is resistant to further accretion. Interestingly, compaction would be favored in the early universe, where gas fractions were high and dynamical timescales were short, the very conditions that also promote rapid early star formation. Webb is providing, for the first time, resolved morphological information about galaxies at these extreme redshift, and some of the early galaxies it is imaging do indeed appear compact, small, dense, with high stellar mass surface densities, in ways consistent with having undergone compaction. But interpreting morphology at these distances is difficult. The angular resolution of even Webb is taxed when imaging a galaxy that subtends an angle of only a fraction of an arcsecond, and distinguishing a truly compact galaxy from an unresolved merger or an AGN-dominated system requires careful analysis. What is undeniable is that Webb is providing us with information about the early universe that no one predicted we would have at this level of detail: the transition from the cosmic dark ages to the epoch of reionization, the period when the first stars and galaxies produced enough ultraviolet radiation to ionize the neutral hydrogen that permeated the universe, has been one of the great unknowns in cosmology, constrained only indirectly by observations of quasar absorption spectra and the polarization of the cosmic microwave background. Webb is beginning to directly image the sources responsible for reionization, and what it is finding suggests that the process was driven by a more complex and heterogeneous mix of sources than simple models assumed. Reionization is itself a complicated story that deserves careful attention. After recombination, the universe was filled with neutral hydrogen. The first ultraviolet-producing objects, early stars, early galaxies, possibly quasars, began to ionize this neutral gas, creating expanding bubbles of ionized hydrogen that eventually overlapped and merged until the entire intergalactic medium was ionized. This process was complete by about 1 billion years after the Big Bang, as established by observations of high redshift quasars whose spectra show the complete absorption of all light shortward of a particular wavelength by intervening neutral hydrogen, the Gunn-Peterson trough, at high redshifts, but not at lower ones. But the details of reionization, what sources drove it, when it started, how quickly and uniformly it proceeded, remain active research questions. One of Webb's goals is to characterize the galaxy population during the epoch of reionization and assess whether these early galaxies were sufficiently luminous and numerous to have produced the ionizing photons that drove the process. Early results suggest that the answer is yes, but with caveats. The galaxies alone may be sufficient, but only if a significant fraction of their ionizing photons escape into the intergalactic medium, rather than being absorbed by the galaxy's own gas. The escape fraction is a poorly constrained parameter, and its value at high redshift has been difficult to measure directly. Webb's deep field observations are beginning to provide statistics on the early galaxy population that are good enough to meaningfully constrain reionization models, and the apparent excess of bright, luminous early galaxies is, in this context, actually helpful. If the universe was more efficient at forming luminous galaxies at early times than we thought, then it was also producing more ionizing photons, which eases the tension in reionization models that previously struggled to identify enough sources. But here's the interesting irony. The same property that makes the early galaxy population challenging for galaxy formation models, the overabundance of bright, massive galaxies, makes it more consistent with reionization completing early and cleanly. The universe appears to have been both more efficient at building galaxies and more efficient at ionizing itself than we thought. These two facts are connected, both products of whatever process was accelerating early cosmic activity, and they push in the same direction. The question of what that process is, what physical mechanism or combination of mechanisms is responsible for the apparently accelerated evolution of the early universe, is one of the most active and contested issues in contemporary cosmology. And I want to be careful here not to overstate the case in either direction. The Webb observations are real, the tension with standard models is real, but we are still in the early phase of accumulating and interpreting this new data. History cautions against drawing too sweeping conclusions too quickly from any single telescope's initial results. Remember that when Hubble first started producing deep field images in the mid-1990s, there were genuine surprises. Galaxies that looked morphologically unlike anything in the local universe, higher than expected merger rates at intermediate redshift, a complex picture of galaxy evolution that wasn't fully anticipated, but those results, ultimately, were incorporated into an updated and improved version of standard cosmology, not a revolution. They pushed the field forward, refined the models, and taught us things about galaxy formation that we hadn't known before. That is, perhaps, the most likely outcome for the Webb results as well. But there is also the possibility, not the certainty, but the genuine possibility, that Webb is telling us something more fundamental, that the tension between the observed early galaxy population and the predictions of lambda CDM is not merely a matter of imprecise parameters or incomplete feedback prescriptions, but reflects a genuine inadequacy in our current theoretical framework. If the most extreme Webb results are confirmed by ongoing spectroscopic campaigns, if the masses and redshifts hold up under the most rigorous possible scrutiny, then cosmologists will need to consider more radical solutions. What might those solutions look like? Some theorists have explored modifications to the initial power spectrum of fluctuations, the pattern of density variations that seeded all subsequent structure. The standard inflation models predict a nearly scale-invariant power spectrum, meaning that fluctuations have roughly the same amplitude on all spatial scales, but some inflationary models predict departures from scale invariance, or even features, bumps, and wiggles in the power spectrum that could enhance the formation of structure on galaxy scales in the early universe. If the primordial power spectrum had more power on small scales than standard inflation predicts, early galaxy formation would be accelerated, potentially explaining the excess of bright, massive galaxies at high redshift. This is a fascinating possibility because it would link the Webb anomaly directly to the physics of inflation, the hypothetical period of exponential expansion in the first fraction of a second after the Big Bang that is thought to have set the initial conditions for all subsequent cosmic evolution. Inflation is itself poorly constrained. There are dozens of viable inflationary models, each making slightly different predictions for the properties of the primordial fluctuation. The CMB measurements have constrained the spectrum of fluctuations on large scales with extraordinary precision, but on small scales, galaxy scales, and below, the constraints are much weaker. There is room in the parameter space for enhancements to the small-scale power that would not violate existing CMB constraints but would accelerate early galaxy formation. Testing this idea requires more than just counting bright galaxies at high redshift. It requires detailed measurements of the clustering statistics of early galaxies, the relationship between their properties and their large-scale environment, and ultimately, better constraints on the small-scale power spectrum from other probes. But it is a scientifically tractable hypothesis, and the Webb observations may be providing the first empirical motivation to take it seriously. There is yet another radical possibility that occasionally surfaces in the literature, and that is worth examining, even if only to show how far the implications can extend. Some researchers have asked whether the current tension in early galaxy formation, combined with other persistent tensions in the standard cosmological model, particularly the so-called Hubble tension, the discrepancy between different measurements of the universe's current expansion rate, might be pointing to a more fundamental revision of our cosmological framework. The Hubble tension is separately troubling. Different methods of measuring the Hubble constant, the number that describes how fast the universe is currently expanding, give results that disagree at a level that is statistically significant and that has persisted despite years of effort to identify systematic errors in either method. The CMB-based measurement, which uses Planck data processed through lambda CDM to infer the current expansion rate, gives a lower value than measurements based on direct observations of the local universe using calibrated distance ladders built from Cepheid variable stars and Type 1 A supernova. Some theorists have proposed that both the Hubble tension and the early galaxy formation problem might be symptoms of a single underlying issue with the standard cosmological model, that the model's treatment of dark energy or the matter energy content of the universe in the early epochs, or the geometry of the universe, is somehow slightly wrong in ways that simultaneously affect both the inferred expansion history and the predicted rate of structure growth. These ideas are speculative and contested, and there is no consensus yet on whether the two tensions are related or independent. But the fact that the standard model is being stressed simultaneously by measurements of the early galaxy population and by measurements of the current expansion rate is, at minimum, uncomfortable. It suggests that if the model is wrong somewhere, the error might be more than a local, easily fixable parameter adjustment. It might reflect something more structural. But let us come back to the galaxy, the specific, faint, impossibly distant galaxy that Webb's instruments resolved and whose light, traveling for nearly the entire age of the universe, arrived at the telescope's mirror and was passed into its constituent wavelengths by mechanisms of extraordinary precision. Let us think about what it means for that galaxy to exist somewhere in the darkness of the early universe, when most of the matter that would eventually form all the galaxies we know was still diffuse, still slowly falling together, still centuries or millennia away from igniting its first stars. There was a region of space that was, somehow, already ahead of schedule, already denser than average, already further along in the process of collapse, already somehow supplied with enough material organized in the right way to begin forming stars at a furious rate. And it did. And those stars lived and died, and the galaxy grew. And after a few 100 million years, only a few 100 million years, a coherent, structured, chemically enriched galaxy existed where there should have been, according to our models, only the earliest stirrings of structure. When Webb looks at this galaxy, it is seeing light that was emitted while the sun, the earth, and every living thing that has ever existed on it was still more than 13 billion years in the future. It is seeing a time before any of the cosmic events that led to our existence had yet occurred, before the formation of our Milky Way, before the first generations of stars that produced the heavy elements in our own bodies, before any of the billions of years of cosmic evolution that created the conditions for life to be possible. And what it is seeing in that unimaginably distant time is a galaxy, not a primordial cloud, not a faint proto-galactic wisp, a galaxy with stars and metals and structure. Already, the fact that this makes our models uncomfortable is not a failure of science. It is science working exactly as it should. Models are not truth. They are our best current approximations of truth, built on the observations available at the time of their construction. When new observations arrive that strain the model, the correct response is not to doubt the observations, but to improve the model. And the process of improving the model, of interrogating which assumptions need to change, and by how much, and in what direction, is how our understanding deepens. What Webb is initiating is one of those periods of productive discomfort that periodically punctuate the history of science, a period when the data outrun the theory, when the questions multiply faster than the answers, when the frontier of knowledge is not a comfortable place to stand. This is, in a very real sense, the most interesting place in all of science, the edge where what we know meets what we don't yet know, and the boundary is actively shifting. The immediate scientific program in response to these observations is well underway. Large spectroscopic campaigns are confirming or revising the photometric redshifts of the most extreme early galaxy candidates. Detailed analysis of stellar populations using spectral energy distribution fitting and stellar population synthesis models is refining the mass estimates and characterizing the star formation histories. Searches for AGN signatures in the spectra of early galaxies are trying to separate the stellar luminosity from the black hole contribution. Theoretical work is exploring every possible adjustment to the standard model that might accommodate the observations without requiring fundamental revision. Some of this work will vindicate the most alarming interpretations, but some will moderate them. The scientific process is iterative and self-correcting, and what we believe today about these earliest galaxies will not be what we believe in 5 years, as more data accumulates and more careful analysis is applied. But certain things seem secure. The early universe was more active than we expected. The first galaxies were more numerous, more massive, more evolved than our models predicted they would be at those times. The process of galaxy formation began earlier and proceeded more efficiently than the standard picture suggested. These conclusions are robust enough that they will survive whatever refinements and corrections come in the next few years. And they are telling us something important about the universe we live in. They are telling us that the conditions for complexity, for the emergence of stars, our chemistry, planets, and eventually life, existed earlier than we thought, that the universe was not as simple or as gradual in its development as we had imagined, that the story of cosmic evolution, which we have been piecing together for decades with ground-based observatories and space telescopes and theoretical machinery of extraordinary sophistication, is not quite the story we thought it was. The universe has been keeping secrets, not maliciously. It has no intentions, no agenda, but as a consequence of the limits of our instruments and the incompleteness of our theories. The limits of our instruments are being pushed back by Webb. The incompleteness of our theories is being exposed. And in that exposure, in that moment of productive uncertainty, when the data say something unexpected and the theorists scramble to understand why, the science is most fully alive. There is a broader philosophical point worth making here, one that extends beyond the specific details of early galaxy formation. Science is often presented to the public as a body of established knowledge, a set of facts that have been determined and settled. And it is that, in part. There are things we know with extraordinary confidence: the age of the universe, the composition of the sun, the mechanism of heredity, the structure of DNA, the speed of light. These are not in question, but science is also a process, and the most interesting parts of that process are happening precisely where established knowledge meets new observation, and the two don't quite fit together. The edge where the model doesn't work is not a failure of science. It is the place where science is most actively generating new understanding. The Webb telescope is standing at that edge, in orbit around the Sun, 1.5 million kilometers from Earth, with its golden mirror chilled to a temperature colder than almost anything else in the solar system. It is pointing at the deepest, most ancient regions of the observable universe and returning data that makes cosmologists rethink what they know. Every spectrum it produces of a confirmed high redshift galaxy is a constraint on our theories. Every galaxy that turns out to be older, more massive, more evolved than expected is a test that our models are currently struggling to pass. The galaxy we started with, that faint smudge of infrared light from near the edge of time, is one data point in what is becoming an overwhelming accumulation of evidence that the early universe was not what we thought it was. It is one voice in a growing chorus of observations, all saying the same thing: revise your assumptions, improve your models, or replace them. Science will do that. It always does. The history of cosmology over the last century is a history of models that were built, tested, refined, and in some cases replaced. Einstein's general relativity replaced Newtonian gravity as the framework for understanding the large-scale universe. The Big Bang model replaced the steady-state model. Inflation was added to explain the uniformity and flatness of the universe. Dark matter was invoked to explain the rotation curves of galaxies and the dynamics of clusters. Dark energy was discovered in the late 1990s through observations of Type 1, a supernovae that showed the expansion of the universe is accelerating, not slowing down. Each of these revisions was, at the time, unsettling. Each required abandoning or modifying something that had been considered established. Each ultimately led to a more complete and more accurate picture of the universe. And in each case, The trigger was observation, data that didn't fit the existing model, forcing a reconsideration. Webb's observations of the early galaxy population may be the next such trigger. The tension is real, the evidence is accumulating, and the theoretical community is actively engaged with the implications. Whether the resolution comes through modest parameter adjustments within lambda, CDM, or through more fundamental modifications to the standard model remains to be seen, but the resolution will come, because that is what science does. In the meantime, there is something worth sitting with, a kind of respectful awe at what the Webb telescope is accomplishing. We have built a machine of extraordinary precision and capability, launched it into space on a trajectory that required years of planning and execution, and aimed it at the oldest light in the universe. And that light, after traveling for nearly 13.8 billion years, has arrived at this machine, been focused by its mirror, dispersed by its spectrograph, and transformed into numbers that tell us about conditions that existed when the universe was barely an infant. The fact that those numbers are surprising, the fact that they challenge what we thought we knew, is not a problem. It is a gift. It means there is more to understand. It means the universe is more complex, more interesting, more full of structure and activity and surprise than the models we had been working with. Every troubling question raised by Webb's observations is a question that, when answered, will teach us something new about the origin and nature of the cosmos. That galaxy at the edge of time, impossibly massive, impossibly organized, existing in a universe that our models say should not have been capable of creating it so quickly, is not an embarrassment to cosmology. It is an invitation to look harder, think deeper, question more carefully, and ultimately understand better. The universe has been around for nearly 14 billion years. It has built galaxies and stars and planets, and on at least one of those planets, creatures capable of wondering about it. Those creatures have now built instruments sensitive enough to see back to within a few 100 million years of the beginning, and what they are seeing is not what they expected. That is, in every sense that matters, wonderful. The questions will continue to accumulate. More galaxies will be found at impossible distances, with impossible properties, demanding increasingly creative explanations. The Webb telescope has years of science ahead of it, and each year will bring new observations, new discoveries, new challenges to the theoretical framework. The community of astronomers and cosmologists who are working with this data are engaged in one of the most profound intellectual endeavors in human history, attempting to understand the full story of the universe from its first moments to the present day. The story is longer and stranger than anyone predicted. The first chapter, which Webb is now beginning to read in detail, is full of surprises, and the troubling questions it raises are not obstacles to understanding, but the leading edge of our understanding expanding into new territory. The light from that distant galaxy, 300 million years into a universe that would go on for another 13.5 billion, carries in its redshifted wavelengths not just the signature of its stars and its metals and its mass, but something harder to quantify, the knowledge that the universe, from its earliest times, was building towards something, not intentionally, not with any plan, but with the relentless logic of physics operating under conditions we are only beginning to understand. And we, who are the universe looking back at itself, are just beginning to see what it has been.